Hello, everyone. My name is Anna. I work at Isovalent, which is now part of Cisco, as a software engineer. I work on observability tooling for networking and security use cases mainly using eBPF. And today I'm going to talk about using eBPF for observability, in particular, how we can use it to transform low-level kernel data into high-level insights valuable for not only sysadmins, but also application developers. So first of all, eBPF is used for observability pretty widely these days, and we've heard a lot of good things about it. That we've been promised that it provides no instrumentation observability, low overhead because it runs in kernel. It provides complete visibility because it can see everything that's happening on the host. And it provides reliable observability. This is a point that I think is sometimes a bit underappreciated because using eBPF for observability means that once we load the eBPF programs and we start collecting the data, they just keep running. I'm sure many of us have experiences of some observability agents going down and or application crashing together with its instrumentation. And when we need, in such cases, when we need observability data the most, we lose it. eBPF doesn't solve this problem magically. It still can have bugs and we still can lose data, but it provides this extra layer of reliability, meaning that once we load eBPF programs and start collecting data, they generally just stay there. But we've also heard a lot of slightly worrying things about using eBPF for observability, like it can produce tons of data. And as a consequence of this, it can be very expensive. eBPF provides a lot of low-level details, what many people are excited about, but are these details really useful for observability use cases for application developers, or are they just providing a lot of noise that makes it harder to extract value from the data? And we also heard that eBPF is generally difficult to use. Writing eBPF code is difficult, but even using eBPF-based tools is often difficult because we don't know how to interpret data. We don't know how to we need how to use the tools. This is a diagram that a couple of years ago it was shown in practically every talk about eBPF. It shows BCC tools collection or eBPF tools, the newer version of the framework for different components of a system. Network components, file systems, kernel, scheduler, memory, application layer 2, drivers, everything. And all of these tools are using eBPF. This diagram was created by Brendan Gregg. These tools are great. They are not easy to use. To use any of these tools, of course, you need to know what it does. You need to know what arguments it takes. You need to know what you want to get from it. Even if you run the tool, you get this very low-level data, and how do you interpret it? If you are troubleshooting application problem or user problem, it's something that was reported to you by a customer, then how does this low-level data help you exactly? And all of this are your problems if you can run the tools, but many of them require root permissions, and many of us don't have root permissions on our production systems for good reasons. We expect from observability tools to provide us observability without need to access production system with high privileges. So observability is a data processing problem. From observability tools, we expect that they will provide us context, correlation, filtering, aggregation, and then we will be able to collect all this data, put it together, visualize it, make it available for developers, for operators, for entire organization, so that we are able to troubleshoot real problems. Can eBPF provide us this? And to answer this question, let's take a look at how eBPF works. So this is a diagram from eBPF.io. There is usually some user space agent that loads eBPF program. Then in kernel, there is eBPF verifier that checks that the program is safe to run. This is an important step that ensures reliability and safety of the tools. The just-in-time compiler makes it fast, compiles it, and then the program is attached to a hook point. Once it's just executed on whenever this hook point is run. There is one piece missing from this picture that is very, very important for observability, and without this piece, eBPF would be pretty much useless for observability. BPF maps. BPF maps are nothing else than just data structures, key value stores in kernel memory. What is important here is that both eBPF programs and user space programs, like the agent that loaded our tools, can access this map. And another thing that's important is that they are generally shared between different eBPF programs. Why it's so important? So let's take a look at how typical observability tools use BPF maps. The first thing is that we need to pass some information from user space to the kernel, to eBPF programs. And what we can pass, absolutely everything. Typically, this would be high-level context, like in Kubernetes, often Kubernetes metadata, queried either from Kubernetes API or it can be from container runtime too. User configuration, user configuring some parameters of what we want to get from the data. Filters are very important here. So all of this information is collected by user space agent and stored in BPF maps so that BPF programs can, for example, access Kubernetes metadata through mapping between cgroup and Kubernetes metadata we queried from Kubernetes API. The second thing is correlation. So different BPF programs attached to different hook points typically use same maps. And this allows us to correlate different events. For example, using tracepoint execv, we can collect information about processes that are executed in the system. And this information can be then used by programs attached to TCP kprobes so that we can correlate program execution containing information, for example, about the program binary and arguments with TCP connections, TCP messages being sent. We also often correlate events for the same kprobe, but when it starts and when it ends. So kprobes and kred probes. This allows us to get full picture of, for example, TCP message that was sent, and provides complete information about this connection to the user. And third thing is We want to somehow get this data from eBPF programs back to the user. This is also done via eBPF maps. The a very common way of doing it is to create an events ring buffer, and then eBPF programs push events through events ring buffer to user space, to the agent. But what we can also do, and what is very powerful, is aggregate in kernel. We can create a metrics map, storing metrics in some sort of format, so that we don't generate event every time something occurs, but we aggregate them in kernel. We reduce the data volume that way, and then user space agent can just read this map as any other metric store, and then export data somewhere to build a full pipeline with data collection, with data visualization, for example, in Grafana, or integrate via open telemetry with all of observability vendors. So this is how eBPF maps are used by observability tools and why they are so crucial. Now, what are these observability tools using eBPF? I will quickly show a few of them, but I will focus on something that maybe not many of you thought of: how to build your own specialized observability tool. There are continuous profiling tools like Parka or Pyroscope, or Pixie. Pixie has many different functionalities. It collects metrics and traces too. Same as Grafana Bela. This agent provides no instrumentation observability, so it injects eBPF-based auto-instrumentation. Cabal is a tool working on top of Cilium that provides network visibility, insights into what's happening on the network layer, both layer 4 and also application layer 7, like HTTP. And there's a tool that I am working on, Tetragon. Tetragon is a tool that was initially built for security mainly. I'm not a security person, but security and observability people tend to do a lot of things in a similar way. This is what I found. So Tetragon is a eBPF-based tool that is very generic, and I will show examples in a moment. It provides internal filtering and also enforcement for security, and it is Kubernetes native. So it provides all this Kubernetes metadata in the telemetry it produces, and also it's configured via Kubernetes custom resources. This is picture on the front page of Tetragon documentation. In this circled area, we see many different use cases for Tetragon: process execution, file access, network activity. We can see everything that's happening in Linux kernel, and possibilities are endless. It is reliable and it provides low overhead. eBPF programs are generally fast, partially because they are just efficient. They are running in kernel, and partially because we don't need to switch between kernel and user space all the time. If we add to this in-kernel filtering and in-kernel aggregation, then we can produce telemetry really much more efficiently than we would do with user space agent. And it is reliable. Thanks to eBPF verifier, we can be sure that it won't crash. Yeah, it provides us complete visibility even when applications are and everything else is on, then the system is crashing. It is portable. It can run on any Linux system in Kubernetes, but also outside of Kubernetes. No problem with this. And it works with any application, with any programming language. Tetragon doesn't rely on any application behavior. It can be used to monitor applications in specific languages, though. And it is transparent. Like you, of course, don't need to change anything in applications, or even if in configuration to monitor them using Tetragon, you don't require any sidecars, any restarts, nothing. What is important from observability perspective is integrations with all the other observability tools, because the Tetragon produce data, but then what you want to somehow process and visualize this data. And Tetragon is typically integrated with security SIEM systems like Splunk or Elastic, like popular open source observability tools like OpenTelemetry, Prometheus, Grafana, but also we saw many people building their own tooling, their own storage using, for example, ClickUp. Tetragon is configured using tracing policy CRD. This is how it looks like. This is example tracing policy CRD for TCP monitoring. We configure what K-probes we want to hook into, what arguments we want to capture. We also can configure filters, for example, filters by Kubernetes metadata. We can say that we only want events produced by this specific application with this specific Kubernetes labels. And for network monitoring, we can filter by IPs that are external to the cluster. So if we filter out the pod services sider and localhost, then we essentially get all the TCP traffic external to the cluster. Now, as you can see, this configuration is very low level. Like you gotta say exactly what kernel functions you want to hook into. You need to understand what arguments they take, what values they return. It is a double-edged sword because this is genuinely difficult to write, but it is very, very flexible. Like this sort of configuration is what allows us to monitor literally everything using Tetragon, while still providing this high-level context from Kubernetes, from application. Tetragon repository and documentation contain many examples, and this is a bit where Tetragon is being used for building custom tools. So I encourage you to check out the policy examples both in Tetragon documentation and the repository. They provide configuration for very specific use cases. Some of them are security, some are more application observability. But if you define such a policy for a specific use case, then Tetragon kind of naturally becomes a building block for more specialized tool. We have data produced by Tetragon, but as I said, we need to somehow collect it and visualize it. How to do this? And of course, there are a million options. The main data format that we get Tetragon events in is JSON events. This is JSON events written to file. This is extremely simple, as simple as it can get. We just have JSONs in a file. But because it's so simple, we can do everything with it. We can plug it to any sort of logs collector. In Kubernetes, we typically use FluentD, FluentBit, or OpenTelemetry, or one of 100 other ones, and export it to any observability vendor or security vendor, or storage like Amazon S3, where we can query data using our own custom tooling. Apart from events, there are also metrics. Typically, we would collect metrics using OpenTelemetry or Prometheus and then visualize them in Grafana or any vendor. But something that Tetragon does maybe differently than many other tools is that it splits the collect and expose steps. The left-hand part of the slide is what we call instrumentation, collecting metrics and exposing them. Tetragon splits it in a way that collection is done in kernel and the Tetragon agent only exposes metrics collected in a map. So what we do with metrics, we can alert on them and we can visualize them on dashboards. Here are example dashboards for tools that I am building using Tetragon for network observability. We see network throughput, TCP throughput with bytes and segments and retransmits and all of this good info. We can monitor network latency too, so TCP round trip time. In all these dashboards, we have Kubernetes metadata filters and also DNS names for external connections, very useful. Binary association, because you remember from the BPF map slide, we actually can get binary names from, for example, execv system call, and then store them in BPF map, and then on any other event, including network events, query the binary names and correlate with them. So this is very useful. Security dashboards. Security teams, they want to have all the data and they want to have low-level data. So eBPF is often perfect tool for security use cases, such as audits for suspicious process execution, for TLS compliance, sensitive file operations, etc., etc. Of course, because this is very sensitive data, security data, we can't just expose it like that to everyone. But because we have application layer metadata, we can gate access to data to such dashboards using some RBAC system based on this application layer metadata. And when all of our observability systems and the dashboards go down, what we can do, we can query BPF map, collecting the metrics using BPF tool. This is terrible. This is a very obscure command where I'm querying key from map using map ID and key in the hex format. This is not how I want to query my observability data. This data is still filtered using configuration passed by the user and aggregated in kernel. It still contains Kubernetes metadata. It's not visible on the slide, but using from a different map, I can still query Kubernetes metadata and correlate it with the metrics. What's important here is that the dashboards show exactly same data and use exactly same tool as we can see using this BPF tool command. So here I'm using same tool for feeding the whole data pipeline and visualization, and for this hacky ad hoc queries using CLIs with root permissions. And this is how eBPF allows us to really bridge this gap between these hacky CLIs that are run by sysadmins and observability tooling, and really valuable observability accessible for developers. And if we don't want to use such low-level tools like BPF tool, then we can still wrap them into more user-friendly CLIs to get raw events directly from BPF map. Thank you for listening. Here I left some links to resources if you want to learn more. and let's stay in touch. There is Cilium and eBPF Slack. This is where eBPF people hang out, and this is where people working on Tetragon hang out too. Thank you.